Kinematics practice problems number 4.
The plot shows the velocity graph of Ben. Draw Ben's acceleration graph for the interval 0 is less than or equal to t is less than or equal to 4 seconds. So what do we know about velocity and acceleration and how they relate to each other? We know that if we have a graph of velocity, the slope at every single point coincides to the acceleration at the same respective point. The way we're going to tackle this problem is figure out the slope at each of these segments and then plot it. First off, from 0 to 2 seconds, what do we have for our slope value? Well, it's not moving anywhere, it's horizontal. The slope of a horizontal line is just 0. But mathematically, let's prove this using the slope equation. Slope, which we're just going to call m, this means definition, so slope is defined as m, equals rise over run. Rise is just how much it moves in the y direction. Run is just how much it moves in the x direction. So in terms of a horizontal line, how much did this line move up in the y direction over this chunk of time? Well, it didn't move up at all. So in this case, m1, which we'll call for this duration, is equal to 0 rise and 2 seconds of run. 2 seconds. 0 over 2 is just, of course, equal to 0. And if we want to be politically correct, 0 meters per second. Now, what is the slope during this interval of Ben's journey? m2 is equal to rise over run, which, of course, is just going to be equal to rise over run. m2, rise, is going to be 6 minus 3, which ends up giving us just this length, which is our rise. So 6 meters per second minus 3 meters per second. It's meters per second because we're doing rise first and we're working with the y-axis, and our y-axis just describes velocity, which has units of meters per second. So not too bad. Divided by our run, which is just going to be this time segment minus this time segment, which gives us this time segment, which is our run. So 4 seconds minus 2 seconds. So m2, our slope, is 6 minus 3 is 3 meters per second, divided by 4 minus 2, which is just 2 seconds, which is just, of course, equal to 1.5 meters per second squared, which is good because that's units of acceleration. Why is it meters per second squared? Because if we have meters per second, put it in parentheses for clarity, divided by seconds, we can just multiply top and bottom by 1 over seconds. Of course, these seconds cancel, and then we get meters divided by seconds squared. But you don't really have to understand that if that doesn't make a lot of sense to you. It's fine. So now let's just graph these slope values. And the way I'm going to do that is by making a plot with correct units, acceleration, which is in meters per second squared, time, which is in terms of seconds, and our time interval is from 0 to 2 seconds and then 0 to 4. And now we're ready to plot. So from 0 to 2, what was our slope value? Our slope value, m1, was just 0. So for this duration, our acceleration value is 0. And then for our second portion, our acceleration is just 1.5 meters per second squared. So I'll just label that arbitrarily here, 1.5. And then right at this moment, we go from 0 meters per second squared to 1.5 for the rest of Ben's journey. So this is how you would plot it, and this is a piecewise function. It doesn't necessarily have to be continuous. These lines don't have to connect, and they don't connect because we went from one acceleration to another acceleration instantaneously in this case, which is technically impossible, but for the sake of the problem, we're going to consider it to be possible. So let's move on to the next problem. All right, here's another problem. The plot shows the velocity versus time graph for a particle moving along the x-axis. Its initial position is x sub I, which equals 3.0 meters at t equals 0 seconds. What are the particle's position, velocity, and acceleration at t equals 1 second, 1.0 seconds? And B, what are the particle's position, velocity, and acceleration at t equals 3.0 seconds? Okay, so the way we're going to tackle this problem is first identify the definition of velocity, because from here we can figure out everything. So average velocity, which I'm going to denote using this bar, equals change in displacement divided by change in time, which of course equals the final displacement minus the initial divided by the final time minus the initial time. What else do we know about velocity and its respective graph? We know that every point on the velocity graph, the slope at every point is equal to the particle's acceleration. That's just a fundamental truth of physics. And we also know that the area under the velocity curve is related to the position or the displacement graph. So let me show you what I mean. First, let's tackle part A and figure out its position at t equals 1.0 seconds. So to do this, let me write down another property of velocity. We know that the final displacement, which is the same as this variable, is equal to the initial displacement plus the area under the velocity curve on some specific time interval. Let's figure that out at t equals 1.0 seconds. So rewriting this equation in terms of our problem constraints, we get final position or final displacement, which is what we're trying to solve for, equals initial displacement, which is x sub I equals 3.0 meters. This was given to us, plus the area under the velocity curve up until t equals 1.0 seconds. So we're really looking at this area right here. Okay, so let's just calculate this area. Well, it's just going to be base times height. So our base is 1 second. 1 second times 4 meters per second. And the units of seconds here, after multiplying, end up canceling, so it works, equals 3 plus 4. So x sub f equals 7 meters. All right, what is our acceleration at t equals 1 second? Well, like I said in the beginning of this problem, the acceleration at this point is equal to the slope of this line at t equals 1 second. So what's the slope of this line? Well, the slope is just 0, and we can prove this using rise over run equation, or the slope formula. The slope formula, m, which equals slope, is equal to rise over run. And in this case, rise, which is how much our y changes over some specific interval, is 0. This line doesn't rise at all in the time interval. On the other hand, this part of the plot does have a slope, which we're going to tackle in part B. So just writing our answers over here, we get at t equals 1.0 seconds, x sub f, which is our position, is equal to 7 meters. V, which equals 4 meters per second. It's literally just reading it off the plot here. And of course, acceleration equals 0 meters per second squared. Part B says, what is the particle's position, velocity, and acceleration at t equals 3.0 seconds? Well, it's going to be the same exact process as we used before. We are now at 3 seconds. Okay, so what's our formula for position? X sub f equals our initial displacement plus the area under the velocity curve up until that point. So that area is just all of this. And what I'm going to do is break this shape down into two shapes. Name one A1 and the other A2. Let's write down our equation. X sub f equals our initial displacement, which again is given in our constraints of the problem, which is just 3.0 meters, plus A1 plus A2, our total area under the curve up until t equals 3 seconds, starting at t equals 0 seconds. A1 is just base times height, because this is just a rectangle. So our base is 3 seconds times our height, which is 4 meters per second. So we figured out this A1, it's just this. A2 is going to be this shape, which I'm going to break this shape down into two shapes, a triangle and a rectangle. This first rectangle is just going to be base times height, which is 1 second. That's this base right here, 3 minus 2. 1 second times its height, which is 2 meters per second. 2 meters per second, plus the area of this triangle. which is just 1/2 base times height. 1/2 base, same as the rectangle, 1 second times our height, 2 to 4 is 2 meters per second. I'm going to rewrite x sub f equals 3.0 meters plus 3 times 4 is 12 meters plus 1 times 2 is 2 meters plus 1/2 times 1 is 0.5. 0.5 times 2 is just 1 meter. So for part B, we have x sub f equals 3 plus 12 is 15 plus 2 is 17 plus 1 is 18.0 meters. Okay, what is our acceleration at this point? Well, the acceleration is just the slope of this line. So we just need to figure out the slope of this entire line, and that will be our acceleration at every point from 2 to 4. So how do we figure out slope? Well, slope, I'm going to just call it the variable m, equals rise over run. So in this case, rise is just how much this line drops from 2 to 4. How much does it drop between 2 to 4? It goes from 4 down to 0. So rise is just going to be 4.0 meters. And since the graph is moving down, it is -4. And run, of course, is going to be how much time elapses during this part of our graph, which is just from 2 to 4 seconds, which is 2. So the slope of our line is just -4 over 2, which of course is just -2 meters per second. A equals -2 meters per second squared. And finally, what is our velocity at t equals 3 seconds? Well, our velocity, we can just read that straight off the graph. Our velocity is 2 meters per second. So our velocity and our acceleration is the same here, but they have different units. So that's the answer to that problem, part A, part B, and I think that just about does it.
Thank you so much for watching the video. Please like and subscribe if you enjoyed what you saw. More problems are coming your way soon. Have a great day.
To run away with me.